Will. So thank you everyone for coming this afternoon. I'll be talking about a recent study that was just published in JGR Planets that used a combination of actually all 5 years of the ARTEMIS data to date and looking at observations by the twin ARTEMIS probes of solar wind protons that have interacted with crustal magnetic fields on the surface of the moon, been reflected away and observed by the spacecraft. And how I took these data, traced them back to the lunar surface, and am able to make a map projected onto the surface of the regions and the amount of solar wind proton reflection that you can get from the moon. And this has a number of implications. It ties to things such as the lunar exosphere, to space weathering on the surface. Bill will talk about that right after this talk. It also has a lot of space physics effects. I don't have time to go into all those details, but I'll show you at least the map itself and what the data show us. So this has been a project in collaboration with Jasper Holakis and Charles Lewa at the University of Iowa, and Shahab Fatemi, who sadly just left Berkeley and returned to Sweden. So we are certainly not the first group to have observed this. This actually goes all the way back to some of the early Apollo data that they had suggestions that these lunar crustal magnetic fields, which are shown here from the Lunar Prospector instrument, that these lunar crustal magnetic fields could actually perturb the solar wind flow. These fields are very small in scale size. They're many, many times smaller than the Earth's magnetosphere, but their strength is actually surprisingly high. In the highest regions, they are at least upwards of 250 nanotesla. You can compare that to the roughly 5 to 10 nanotesla strength of the solar wind magnetic field. But it's even suspected that this 250 is sort of a lower upper bound, that in fact there are regions of small-scale magnetism that actually go higher than 250 nanotesla. There's been some very recent modeling work done, or observational work done by Charles Lewa. This is using Chandrian data, and what you're seeing here is a map of the far side of the moon. The bright red color is actually the amount of reflective protons that you're seeing coming up from the surface. And if you look closely enough, these black contours are the associated crustal magnetic fields underneath, and you can see there's a very high degree of correlation between the location of these crustal fields and where we see these protons coming back up. These are in charged form, but actually there's another instrument that was on the Chandrayaan-1 spacecraft that looked at energetic neutral atoms. So these are solar wind protons that are initially charged. They come into the surface. They interact with the grains themselves, and they happen to steal an electron. They become neutral, but they go out at very high speeds. And shown here is sort of a single orbit worth of flux, and these little lines that are coming off is the amount of reflected flux. And that was a very interesting finding from Chandrayaan. What's interesting even for this case is that over the regions of crustal fields, you actually see a decrease in the energetic neutral atoms. And so what's happening is these crustal fields, they're reflecting the charged protons before they can get to the surface and transform into neutral atoms. And this is sort of a cartoon that was drawn by the Kaguya folks, Saito-san et al. In 2012, about just how exactly the physics works for this reflection. You have the lunar surface. You have a small region of crustal magnetic anomaly fields on the surface in the incoming solar wind field. And what happens is that the scale and the strength of these magnetic fields is efficient enough to magnetically mirror electrons. So electrons come in, there's a magnetic mirror force in regions of strong crustal field, and they leave and go back outwards to the solar wind, but the solar wind protons here in green are just large enough that they don't really interact with the crustal fields directly. They have a little bit too large gyro radii. And what happens is this sets up what we call a charge separation, where the electrons are typically at higher altitudes, the protons penetrate down to deeper altitudes, and you build up a static electric field. And that electric field can actually be very strong, relatively speaking. It's strong enough actually to halt the solar wind and turn it back around, or at least a significant fraction of the solar wind. Direct observations of this electric field are few and far between. And there's really only one observation that I know for sure, which is in this Saito et al. Paper in 2012. And really what ARTEMIS is doing is ARTEMIS is typically at higher altitudes. We don't actually see this electric field. What we see in this green arrow, we see the protons come basically spraying back up off the surface. And that's the observation that I'm compiling today. Okay, so how is it I go about doing this? So the ARTEMIS probes, there's 2 of them. There's a little cartoon here and another one. They are identical probes. They have everything that a plasma physicist would want, or almost everything. We have low energy ions from about 1 eV up to 25 keV. We know the magnetic field with very high time resolution. We also, from that, can determine what the solar wind convection electric field is, which is important for knowing how protons undergo gyration in the field. We have periselene passes. The lowest altitude is anywhere from about, well, 10 kilometers is quite low. Typically, they're somewhere between 10 and 1,000 kilometers altitude. One orbit of each ARTEMIS probe takes about 24 hours, and they're exploring all regions of the moon, all solar zenith angles, all local times. And at the time that we published this study, we had about 5.5 years of continuous operations. So I basically took the ARTEMIS data, and I'll show an example in just a minute, and picked out every time we saw reflected protons and mapped it back to the surface to see where and how much we were getting reflection from the crustal anomalies on the surface of the moon. So what does an example of the ARTEMIS data look like? If you start on the left here, you see this is an orbit looking at the, or a figure looking at the Earth's magnetosphere. The black solid line is the Earth's bow shock, so anywhere to the left of that downstream is the terrestrial magnetosphere, and everything upstream of here is out in the pure solar wind. And on this day, the moon was off on one of the flanks. It's very far out into the solar wind, so we don't have to worry about the terrestrial magnetosphere messing up with any of our measurements. The lower left plot here zooms into just around the moon. The dashed line going behind the moon is sort of the lunar optical shadow, or downstream of the moon. And these are the two orbits over about an hour of the two probes. So you can see P1 for probe 1, ARTEMIS 1, kind of starts off the side and actually passes right over at a fairly low altitude over the side of the moon, while P2 during this time is fairly far away and off to the flank. Now you notice also this little tick mark I've put here, that's the location of the far side of the moon. It's also the location of the South Polar Aitken Basin, which is one of the stronger regions of crustal magnetic strength on the moon. And so you see ARTEMIS did a nice flyby right over that region of crustal field. What we actually observed is shown here. These two top panels are ion energy spectra. So the y-axis here is energy. So the higher up you go, the more energetic the ion. The x-axis is time. This is about an hour's worth of time. And if you look first at this panel right here, this is what P2 is measuring. This is basically just showing you the roughly 1 kiloelectron-volt solar wind. That's all that it's seeing off to the side of the moon. It's a quiet day in the solar wind. We see nothing but this bright beam. However, P1, the probe that's much closer to the surface, sees all this fuzz that's coming up on top and even coming down. Those are the protons that have gone all the way to the lunar crustal magnetic field. They've interacted with these electric and magnetic fields and come spraying back off. And that's the stuff that I'm really interested in. So we can actually break that apart even a little bit more. And what I did is I took that same set of data where we were seeing these crustal fields, and these top two panels essentially show, just now looking in direction, these are the protons only coming from the direction of the sun. They're almost exclusively the solar wind. And this second panel here shows the protons that are only coming from the direction of the moon. So they've interacted with the moon, they come spraying back up, they hit you in the face, and this is essentially what we see. All of this structure is actually telling us about the strengths of magnetic fields on the surface. So these protons have somehow interacted with those fields. Meanwhile, you can compare it to these lower three plots, which is actually the reference probe that's much farther from the moon. You see, again, we see the solar wind beam, and essentially you see nothing. These are actually background counts in the instrument. So we definitely, by virtue of having two probes at the moon, one slightly farther away, one up close, I can tell you that this population of protons really does come from interacting with the moon. And it doesn't come from CME from the sun. It's not coming from the terrestrial magnetosphere. And that's one of the really beautiful parts of the ARTEMIS data set, is we know exactly what comes from the moon and what doesn't. The one last thing to note about this population here is it's actually about 20% of the solar wind, actually. So this small region of crustal magnetic field is able to turn around a fairly significant fraction of the solar wind. So the question is, where did all these protons come from? Well, there's a French mathematician named Joseph Louisville, and he tells you that if you trace back using the magnetic and electric fields, you walk time backwards and you follow where these protons come, I can actually tell, I can relate the amount of proton flux that I observed at the ARTEMIS probe to what came off of the surface. What I'm showing you here is an example of a single time frame where I'm tracing protons that went in every direction, and the subset of trajectories that I've highlighted in red are actually the ones that came from the moon. So anywhere else must have been solar wind or zero flux at all, but anything that came from these directions in red is actually protons that have interacted with the lunar surface and come back up. So what I'm showing you here is, maybe 30 observations or so that I've traced back. I actually took the whole data set after a while, and that ended up being 1.5 billion times we did all of these little trajectories. So all of the computers at Berkeley were busy for like 6 months doing all this. For this individual example, though, I can show you exactly where we measured. This is now the lunar surface. These little black lines are the crustal magnetic field. This big blob right here is the South Polar Aitken Basin region. This is all the region where ARTEMIS could actually quote-unquote see. Anytime a trajectory traced back to the surface, regardless of how much flux was there, I put it in this map. From there I said, okay, of all these trajectories that map back to the surface, which of the ones saw the most proton flux? And that's what's shown down here in the lower panel. And you see there's this bright spot. All the rest is black. There's no protons that really come from there. But this one spot is nice and bright, and actually it sits just on the shoulder of the South Polar Aitken Basin magnetic anomaly. So that's really where we're seeing a nice proof of concept that these crustal fields really do reflect a significant chunk of the solar wind. So what happens when I go from just this single day to the entire data set? This is 1,600 ARTEMIS flybys of the moon. Like I said, it's 1.5 billion individual measurements of protons that we took and traced back. And essentially, if we just look at the bottom panel, this is what the moon looks like if your eyes could see protons. That's the way to think about it. The center region here is actually the South Polar Aitken Basin anomalies on the far side. You see that's the brightest patch, but you can actually see a couple others. This is the Oriental Antipode. Actually, I have a zoomed in map. Here we go. This is the South Polar Aitken Basin. This is the Oriental Antipode. This is the Gerasimovich anomaly right here. Little Rhina Gamma is right here. And you can see that these fluxes are getting anywhere on average about 12%, at least at this fairly coarse resolution. But what this does is this actually really tells us that the Chandrian measurements weren't a fluke at all. We really are seeing a pretty decent sized reflection from a lot of these crustal fields. You do see some crustal fields that don't have much reflection. The thought is maybe they're just a little bit too weak. Maybe the topology, the way the crustal fields are arranged, are actually somewhat unfavorable as opposed to some of these other guys. That's actually an open question, why we don't exactly see reflection from every little bit of crustal magnetic field on the surface. But in fact, you can actually see some from smaller ones like Gerasimovich. The Rhina Gamma anomaly that's right here is actually one of the more famous ones because of its association with lunar swirls on the surface, which are thought to do with some amount of solar wind standoff and reflection. It doesn't show up too much on this plot, but that is actually a quirk of the processing, that Rhina Gamma is actually very, very small. It's about 1 by 1 degree. And these boxes, what ARTEMIS can basically resolve is 5 by 5 degrees. So Rhina Gamma is one piece of this little bit of reflection. But nevertheless, we actually do see protons reflecting even at a fairly low rate. I've got a few minutes left. We can also actually tell you the directionality that the protons are reflecting off. The long story short of this is actually these are the data in basically the sky map, what directions the protons go off, and you can see they're kind of scattering in all directions, which is very similar to what the cartoons are. This is simulations by Mike Zimmerman et al. That show. So there's a nice, good agreement between this. This is really just the beginning of this data set. This is sort of the global view of it, but we can actually drill down and we can look at any of these individual anomalies. We can start to look at how the reflection percentage changes as a function of solar wind density, solar wind speed, solar wind pressure. And the data set is fairly robust, actually. Again, these 1.5 billion measurements that went into it, and actually continuing because ARTEMIS keeps going. So with that, I'll actually throw up the summary. We know that the moon has crustal magnetism. We routinely see these reflected solar wind protons with ARTEMIS. I mapped them back using some Louisville tracing technique, which is fairly standard. And again, we can see these regions that reflect somewhere between 10 and 15% of the solar wind on average. But really from here, there's a lot more to do to dig into a lot of these individual anomalies and trying to understand why some reflect more than others and how that changes with solar wind condition. So I think I'm roughly out of time. So thank you.
All right, any questions for the speaker? We have a few minutes for questions. Diane, here you go.
Diane Wooden. I was curious if there's a geological feature associated with like 60 to 80 degrees latitude and around 360 degrees longitude. There's like sort of an enhancement there.
This guy?
Yeah.
So the thought with this is essentially the near side, right? And most of the near side, if you think about it, doesn't get the full brunt of the solar wind because as the near side is on the day side, then it's in the terrestrial magnetotail. So I'd be a little hesitant to interpret some of these points because actually it really isn't ever seeing the full blast of the solar wind, which is what this technique is really designed for. Even then, this is down at 1% of the incoming proton flux that could just be down in the noise as well. So I don't necessarily think that points to anything significant.
So in this map here, the little black outlines, what are those?
These little squigglies?
Yeah.
Those are the crustal magnetic field strength at the surface, and I think the contours were 20, 30, and 50 nanotesla. So Rhina Gamma shows up as one of the strongest guys, for example.
So, I'm looking at that map, and there's the SPA, and there's the yellow part that's kind of away from where your
This guy? Mm-hmm. Yeah.
Josh Cahill is doing some analysis of the LAMP data and finding new swirls that are beyond what were identified with the LROC data set.
Interesting.
In that region there.
Yeah, so it's possible then that I actually wondered, actually,
he's pointing.
Jasper asked me essentially the same question. He's like, what are your protons doing here? And I didn't know. I used the same tracing code to do everything, but it's possible that the map itself is from Lunar Prospector, the electron reflectometry, so it's possible it missed some regions of crustal field, so they're not showing up as black contours, but I'd be really interested. This is actually, if you want to go look at the map, it's all published in JGR Planets now, so you can go stare at it as much as I have if you really want. So, okay.
All right, very good. I think
Think we're good?
we're good. Hey,
Should I trade you?
yep, there you go. Let's go. All right.